is 40 Days of Chemistry, part 25, this time going right back to production materials, 9.2.4, looking at batteries. And the first thing we looked at in this topic was metal displacement reactions. And you need to know the definition of metal displacement reaction, but more importantly, you need to know how it works. And in a metal displacement reaction, the more reactive metal is oxidized, and the ions of the less reactive metal are reduced. And so, for example, if you put copper solid in sodium ions, there is no displacement because the less reactive metal is already the solid form. But if you put zinc inside silver ions, the more reactive metal zinc will displace the less reactive metal ions, silver ions, from the solution. So you will get metal displacement. And it's a really tricky question. It was actually in shipwrecks, corrosion and conservation. There was this question: you've got a bit of magnesium and a bit of iron inside a solution, which is a mixture of magnesium sulfate and iron sulfate. Describe what would happen in the experiment and include relevant chemical equations in your answer. So have a think about it and pause the video, write down what you think the answer is, then press play and see what the answer actually is. Okay, so let's have a look at what actually happens. And first of all, you will get metal displacement at the magnesium because you've got magnesium, which is a more reactive metal, and you do have this iron sulfate in solution. So you will get metal displacement there, and you get magnesium displacing the iron, so you'll get solid iron precipitating on the magnesium. You won't get metal displacement of the iron because iron is less reactive than magnesium, so there will be no metal displacement of the iron, but you will get rusting at the iron. Okay, so you use the rusting equations, and the reason why you get rusting is because you've got iron in an aqueous solution. There's going to be oxygen in the water, and therefore that will just rust. And the reason that the magnesium isn't protecting the iron from corrosion is because they're not in contact, and because they're not in contact, that means there's no galvanic cell, which means there's no cathodic protection. So quite a tricky question there. Moving on. Redox and oxidation numbers. Now, redox reactions involve one species losing electrons, which is the reductant, which is being oxidized, and one species gaining electrons, which is the oxidant, which is being reduced, and you have electron transfer from reductant to oxidant. And when redox occurs, you get a change in oxidation numbers. The species that's oxidized has an increase in oxidation number. The species that's reduced has a reduction in oxidation number. Now, oxidation numbers have a whole lot of rules. I'm not going to talk about them here because you can read them in your own time. You should know the oxidation number rules, and you won't be asked questions about the rules. What you'll be asked questions about is, can you figure out oxidation numbers, and then can you use oxidation numbers to figure out if redox has taken place. So there's two little practice activities there. First of all, what's the oxidation number of manganese in this compound, and is this a redox reaction? So have a go and pause the video and press play when you're ready to have a look. Okay, so what was the answers here? Well, in this particular example, potassium is always +1, it's an alkaline metal. Oxygen is -2 in all compounds, therefore manganese must be +7. And down here, look at the carbon. It's gone from -4 in the methane to +4 in the carbon dioxide, therefore it's been oxidized. Nothing's happened to the hydrogen, it's in compounds with nonmetals both times, so it's +1. And the oxygen's gone from 0, which is the element, to -2, so oxygen has been reduced. So yes, it is a redox reaction. And while we're here, this is a fantastic little game. It's a mahjong game to do with oxidation numbers, and it's also to do with balancing equations and a whole lot of different factors you can select with this little thing here. It's at this website here. I might send you a link for that later on as well. Galvanic cell design. If you separate the reductant and the oxidant, and you put a path there for electrons to travel through, you can make electrons travel from the anode to the cathode, producing useful electricity. But you need to have a reductant and oxidant, which means you need two different electrodes. You need a conductive path between them for electron transport, and there needs to be an electrolyte between them for ion transport to maintain charge neutrality or just complete the circuit. And don't forget the sayings: oil rig, oxidation is loss and reduction is gain. Red cat, reduction occurs at the cathode, which is the positive electrode, and angry ox, anode is the negative or angry side of oxidation. So here's a typical galvanic cell. You've got the silver cathode here, you've got the lead anode. How do we know that silver was the cathode, lead was the anode? It's because silver is a less reactive metal, lead is a more reactive metal, or silver has the higher reduction potential, lead has the lower reduction potential, or simply by the ABC rule, anodes before cathodes, which you can use on your standard reduction potential list. In this situation, being the cathode, the silver is positive, being the anode, lead is negative. You get electron transfer from the anode to cathode. You have cations going through the salt bridge from anode to cathode. You have anions going through the salt bridge from cathode to anode. The salt bridge, it's usually a potassium nitrate aqueous solution. It completes the electrolyte connection, allowing charge transfer between electrodes, anions to anode, cations to cathode. But why choose potassium nitrate? It's because potassium and nitrate form no precipitates, therefore they won't clog up the salt bridge. You'll always have ions in solution ready to conduct electricity, and they don't undergo redox reactions either, therefore they're not going to interfere with the operation of the cell. And don't forget, you can write these cells in shorthand. There's the example of the shorthand for this particular cell. Moving on to looking at the electrodes. I don't think you'll ever need to know or answer a question specifically about electrodes, but you need to be aware that there's different types of electrodes. First of all, the most common sort of electrode is you've got a metal in the solution of metal ions. We saw that in the previous example. Sometimes, though, you have an inert electrode, such as platinum or stainless steel or graphite, sitting in a solution of two forms of a metal's ion, an oxidized form and a reduced form, and that means the redox reaction is going to take place between the ions. Either one's going to take electrons together, or vice versa. You can also have inert electrodes sitting inside a solution of an ion, in this case chloride ion, while its gas is bubbled over the top at 1 kilopascals, and therefore you can have redox reactions taking place between the ion and the gas on the surface of this inert electrode. Note the standard hydrogen reference electrode is an electrode just like this one, except in the standard hydrogen electrode you've got hydrogen gas bubbling in, and you've got hydrogen ions in solution. The hydrogen ions at 1 mole per litre, and the hydrogen gas at 100 kilopascals, which are the standard conditions for galvanic cells. So looking at galvanic cells and E0, those standard reduction potentials we talked about, they're the potential of that particular half cell relative to the hydrogen reference electrodes. If you get a negative potential for E0, that means that cell acts as an anode with respect to the hydrogen reduction cell, but if you have a positive E0 value, that means it's acting as a cathode when you put it in connection with the hydrogen reference cell. But you can use those standard reference cells or the standard reduction potentials to figure out the voltage of any given cell. And there's a series of rules which you always use to figure out the E0 value of a cell or the cell potential. The main one is once you figure out the anode, you have to reverse the reaction because the reactions on the reduction potential sheet are all reductions. The anode is an oxidation reaction, therefore you must reverse the anode reaction, and therefore you must also reverse the sign of the anode reaction as well. Then you just add the reduction potential plus the oxidation potential, and that gives you the cell voltage. When you're calculating the whole cell reaction as well, just make sure that you need to make sure electrons are balanced in both half equations before you put them together to make the overall cell reaction. Don't forget, if you're getting stuck, the ABC rule works on the standard reduction potential list. Anodes before cathodes. The anode reaction will always be one close to the top and the cathode the one close to the bottom. So why don't you pause the video now, have a go at this question, and then come back and press play and see what the answer is. Okay, so looking at this one, the cell reaction at E0 for this particular cell, what I figured out was that the silver would be the cathode, therefore the silver would be reduced. So I've got 2 silver ions plus nickel goes to 2 silvers plus a nickel ion. I had to double the silver reaction because it needed to have 2 electrons to balance the nickel reaction, and I found the cell potential was 1.04 volts, and I hope I haven't made a mistake there because I forgot to double check. Let's move on. Experiments. We did 2 experiments to do with galvanic cells. The first one was the conditions of a galvanic cell. We got zinc and copper strips, filter paper, we had a whole series of solutions, water, metho, oil, potassium nitrate and sodium chloride solution. We only got a voltage when we had different electrodes, so copper and zinc, not copper and copper or zinc and zinc. There had to be an electric contact and also an electrolyte, so there's potassium nitrate or sodium chloride there. The biggest trick with this one was what was the actual reaction taking place. Have a careful think about this. What's the cell reaction and what would the E0 of this cell be? So have a go and pause the video, press play when you think you got it. Just don't fall for the tricks for this particular one. So what are the 2 electrode reactions? Well, the first one's pretty straightforward. You're going to have zinc taking place. So zinc is going to be oxidized in this particular cell. Let's get that out of the way. And what's going to be reduced, though, the most common mistake is to say that copper ions will be reduced to copper. And that would be true if there were copper ions there, but there's no copper ions there to be reduced. The only thing we've got there to be reduced is oxygen from the air dissolved into the filter paper. So just like in rusting, the actual reduction equation is the oxygen reduction equation, which is that, and therefore the cell potential should be 1.16 volts. The other experiment we did was galvanic cells and E0, and I haven't checked my spelling here unfortunately, and with galvanic cells and E0 all we did was make different solutions or different half cells with metals in their solutions, and then we connected them together with salt bridges to measure their potential. We had to sand the samples first to accept lead, we had to wear glasses and gloves because of the lead and silver solutions. There were some errors, there were some surface contamination impurities which changed the E0 values, and also the solutions weren't always at 1 mole per litre, therefore we had differences between the measured values and the supposed E0 values. The dry cell, this is just in slides we use to look at the dry cell. You need to have a general idea of the structure of the dry cell. You need to know the 2 equations of the dry cell, and when you put them together, don't forget you've got to double the cathode reaction because it's got only 1 electron, whereas the anode has 2 electrons. The good points of the dry cell are here. The slightly negative points are here, which is why this equation is so important because that covers the negative points, and there's the cost, practicality, and impact on society. Same thing for the silver button cell. You need a general idea of the structure. You do need to know the 2 half equations. You need to know the good points about it, which relate to the 2 half equations, particularly the fact that hydroxide ions are consumed and produced at the same rate, therefore there's no drop in electrolyte, therefore the voltage stays constant. It does have some negative sides, and the main points as far as the syllabus is concerned there. And so that is the end of 9.2.4.